Welcome to solverfy.
We're asked to determine whether the given graph is planar, and if so, to draw it so that no edges cross. So we're given a graph on 6 vertices, labeled A, B, C, D, E, and F. And we have edges AC, AD, AE, AF. As well as edges BC, BD, and BF. Edges CE and CF. Edges DF. And edges EF. Now, notice that given graph doesn't have a subgraph homomorphic to K5. And to see why, this is because 2 of the 6 vertices in this graph have a degree of 3. So notice that B has a degree of 3, D also has a degree of 3, E has a degree of 3, and we know that K5 requires 5 vertices of degree 4 each. Now, notice that the given graph also does not have a subgraph homeomorphic to the complete bipartite graph K33. And this is because there are not 3 vertices that are connected to all remaining 3 vertices in the graph. So for example, say we pick vertices A, B, and C. Well, we see that A is connected to F, E, and D. B is only connected to F and D, so we can't have that. Notice that C also was only connected to F and E. And so you see that if you choose any 3 vertices, you won't be able to find any that are connected to all the remaining three vertices in the graph. And therefore, by theorem 2, it follows that the graph is planar. And so we should be able to draw this graph without any crossings. So to do this, there are a few different ways, but one easy way is to notice that we could move vertex B below all the other vertices and move vertex E above all the other vertices. So I'll move vertex B down here. I should draw this in green. And I'll move vertex E up here. And I'll move all their edges with them. So we have now B is still linked to F, and B is still linked to D, and B is still linked to C. So I can get rid of the rest. And we have that E is still linked to F. Rather than doing my mistake. E is still linked to F, E is still linked to A, and E is still linked to C. And now we see that there's only one crossing remaining, which is between edges AD and FC. So to uncross these, let's replace the straight edge between C and F by a curved edge. So we can take this edge and simply go around. For example, we could go above vertex E. And so we have